Hello, welcome to the low power VLSI video lecture. In this lecture, we'll discuss about the ideal and practical characteristics of a inverter. Consider this waveform. This x-axis is the input axis and this y-axis is the output, representing the output. When you increase the input, when the input is at 0, output is at VDD, which is the basic property of the inverter. As you slowly increase the input from 0 to its maximum VDD, the output drops from 1 to 0 exactly at the midpoint of this x-axis. That is, when the input voltage is varied half of the maximum, its output drops to 0. The point at which output drops to 0 or at which output shifts from 1 to 0, that point is called as the threshold point of the ideal inverter. But practically, it is not similar to the ideal curve. There is lot of change, a lot of difference in the ideal and practical curve of a transfer curve of a inverter. These curves which we have seen and which now we are seeing, both are called as transfer characteristics of a inverter. Transfer characteristics of the inverter. Now if you see the practical characteristics of the inverter, when the input is low, as we discussed, output will be high. But practically, the output will not be at VDD, but it will be a little less than VDD, because there will be a little drop at pull-up device. Because of the pull-up device, there will be a drop which is very little. So maximum output voltage for level 1 will be VOH, which is slightly less than VDD. So here you can see the statement VOH is the output high voltage. VOH stands for output high. That is maximum output voltage level for output level 1. When you slowly change the input from 0 to high, when the input reaches VIL, input high voltage, this is the 0 is treated as logic 0 as input, 0.5 volts, 1 volt, 1.5 volt, like that. As you are progressing, increasing the input voltage and you are progressing ahead, some levels of input voltages are treated as logic 0, in spite those are not 0. As we have seen in the ideal case, exactly at VDD by 2, the output has dropped from high to low. Here at VIL, the output drops from high to low in ideal case. But in practical case, the output slowly drops from high to low. This low VIL is input high voltage, is the minimum input voltage which can be treated as logic 0. So this voltage till 0 to VIL we can treat as logic 0. Beyond VIL, it is not treated as logic 0. And the line which is having 45 degree slope is V in is equal to V out curve. This curve is decreasing slowly, and when this curve touches the point V in is equal to V out, that point is called as threshold point of the inverter. This point is called as threshold point of the inverter or inverter threshold voltage. Now the voltage will drop to 0. This VOL, output low voltage, is the minimum output voltage for output logic 0. So this should be the minimum voltage to be treated as 0. If it is above 0, above VOL, here it is not as treated as 0. Under this curve, under VOL, output is, you can say output is 0. If it is more than VOL, you cannot say output is at 0. That is the meaning. VOL is the minimum output voltage at logic 0 level. Now VIH, as the curve progresses VT and comes down, it will touch a point. The point is VIH, the maximum input voltage that can be accepted as logic 1. So from here till this point, till VIH, it is not 1. It is till VIL it is 0. Till VIH it is not 1. Above VIH it is 1. From VIH to VDD it is treated as logic 1. So if you see these statements, following statements, you will understand these voltage levels and all very clearly under the heading noise margins. The allowable noise voltage on the input of a gate so that the output not affected, that is called as noise margin. If you can remember in the previous slide, logic 0 is treated as a voltage which is treated as logic 0 at the input, that is on x-axis is 0 to VIL. 0 to VIL it is treated as logic 0. VIH to VDD it is treated as logic 1. In the output curve in vertical axis, 0 to VOL is treated as output 0. VOH which was at the top to VDD, which is very less margin, that is treated as logic 1. I think it is clear now. Now low level noise margin is defined as the difference in the magnitude between the minimum low output voltage of a driving gate and the maximum input low voltage accepted by the driven gate. That means if you are driving another gate, that gate should not expect exact 0 volts from you for a logic 0. There should be some margin. If we are talking about the margin at low level, that is logic 0 level, then it is called as low level noise margin. The difference of magnitude between the minimum low output voltage VIL of the driving gate and the maximum input voltage that can be accepted for a driven gate. So this is low level noise margin. Similarly, coming to the high level noise margin, the difference in the magnitude between minimum high output voltage of a driving gate, that is output of a gate, minus the input which it accepts. next level, minus the minimum voltage acceptable for the high level by the driven gate, that is VIH. These are